Nossa. Vamos fazer isso tudo. Ok, então.
Agora sim.
Ah, tá ótimo.
Eu coloquei esse... Outro dia dei uma palestra no CIMAT, em Guanajuato, com o Renato Iturriaga, e coloquei esse fundo de tela aí. E deixei todo mundo com inveja. Você tá muda, Zezé?
Marcelo, como é que você coloca fundo de tela no Zoom ou o que seja? É na conta que entra? Ou...
Não, nem na tela, na sua frente tem um lugar, já não lembro qual é, mas tem um lugar para escolher fundos de tela. Eu não consigo...
tá. Depois eu pesquiso, então, deixa para lá.
Aí
Depois eu te digo, Zezé, acho que
Tá.
você pode escolher.
Olá.
Ei, Pedro.
Olá, Marcelo, tudo bem?
Tudo bom?
Oi, Pedro.
Olá.
Mas, ô Marcelo, a sua tela tem movimentos.
Tem, por isso que eu gosto dela. Parece
tipo
verdade,
um filminho.
Né? O MIT também tem telas, e você pode usar as suas também, mas para quem não é especialista, tem uma dúzia de telas, mas são estáticas, né? Essa aqui é muito mais legal, né?
Claro, porque dá uma impressão que você está aí na praia, pessoal lá naquele frio, na Europa.
De fato, eu estou mesmo. De fato, eu estou mesmo. Para não deixar vocês com inveja, eu estou dizendo que é fake, mas de fato é isso mesmo.
Acho que você deixou a gente com inveja mesmo dizendo que é fake.
Eu tenho que comprar um ventilador, botar um ventiladorzinho daqueles pequenininhos de cabeceira para soprar o cabelo e tal, para tornar mais realista.
Isso. Aí põe um abajur assim, com uma luz que aí você tem, olha, está muito sol, tem que sair, pegar sombra.
O MIT tem um fundo de tela que é legal também, é uma foto da galáxia. Então você fica assim com uma pose bem impressionante.
Vamos ver.
Eu saí, né?
Sim, a apresentação.
Caiu, né? Deixa eu ver se volta agora. Você viu cair.
Efeito da praia.
Foi mesmo. E agora? Está no e-mail.
Tudo assim.
Vamos esperar mais uns minutinhos, uns 3 minutinhos, para você entrar.
A Vanessa. Oi, Vanessa.
Olá!
Tudo bom?
Tudo bem, Zezé? Tudo certo por aqui? Como você está?
Então, também muito bem, indo.
Na medida do possível, né? Administrando aqui, né?
Administrando bem. Fazer o quê?
E aí, Vanessa? Saudade de você, viu?
Olá! Oi, Lu!
Baiana.
Tudo bem, Lu? Minha cantora preferida.
Agora tá melhor, vendo amiga.
Quanto tempo, hein?
Veja você o que não é a doçura de uma baiana, né? Já chega trazendo luz.
Calma, gente, tudo vai dar certo.
É ótimo trabalhar com a Vanessa, porque ela sempre acha que dá para provar. Não, Vanessa, a gente achou um erro aqui. Não, calma, tudo vai dar certo.
Gente, tem que manter o otimismo.
A gente tem que ser otimista, com certeza.
E o Ícaro, tá bem?
Tá bem, tá enorme. Eu ainda não conheci a Ana Luísa, pessoalmente, mas em breve eu morderei todas as dobrinhas dela.
Com certeza, com certeza. Muito
Você
bom,
só vem aqui
Deus.
na correria, poxa.
Né? Quando a gente tem filho pequeno, sabe como é, né? Tem que ser correndo. Mas os filhos crescem, né, Lu?
Certamente, certamente.
Muito bom revê-las.
Let's start. Okay.
Yes.
Well, so it is my pleasure to introduce Marcelo Viana from IMPA. And even that Marcelo do not require introduction, but it's worth to speak something. And Marcelo is the director of IMPA, and he also helped the development of mathematics in Brazil during his career in so many ways. So he published many important articles, and he was the supervisor of many students. Some of them are here, and also actually I had the honor to be one of them. And he also helped to perform many congress, I believe, if not on all of the states of Brazil, and almost all states, and especially the International Congress of Mathematicians in 2018, where he was the main chair of the Congress, which held in Rio de Janeiro, and it was a landmark to the mathematics of Brazil. So I'm very happy to introduce him, and he also is a very good friend of UFRJ. And today he will talk about two issues in partially hyperbolic dynamics. And well, thank you, Marcelo.
Thank you very much, Alexander. And thank you all for being here. Jacqueline, I'm going to ask you to allow me again to, for some reason the presentation fell, and now I don't have permission anymore. The second user, okay? It's again.
I hope it's working already.
Let's see. Yes, it is. Okay, so again, thank you very much. It's a pleasure to be with you all here. I want to congratulate Alexander, Jacqueline, and all the others at UFRJ for setting up this meeting. I want to discuss in a very informal way, as informal as possible, two particular issues in partially hyperbolic dynamics. It is the presentation is based on work I've done with Arthur Avila and Amy Wilkinson. Part of it has been published a couple of years ago already, and another part is just coming out now in the volume, in the issue, or a couple of issues of ergodic theory and dynamical systems dedicated to Anatoly Katok. So I didn't know what the audience would be. Probably most of you know what a partially hyperbolic dynamical system is, but still I will start with the definition. A diffeomorphism, so a partially hyperbolic diffeomorphism is a diffeomorphism on a compact Riemann manifold, such that one can find a continuous decomposition of the tangent space into three subbundles. Continuous means that these subbundles depend continuously on the base point x, and this decomposition should be invariant under the dynamics, which means that each subspace is mapped to the corresponding subspace at the image point, as is spelled out there. And the reason why we call it partially hyperbolic is that the three subbundles should have very distinct behaviors with respect to the dynamics. The so-called stable subbundle ES is contracting, meaning that the derivative, the restriction of the derivative to this subbundle should be uniformly contracting. Similarly, or dually, the unstable subbundle is uniformly expanding, which just means that if you apply the inverse of the dynamical system, if you consider the inverse, then the EU behaves as a stable subbundle for the inverse. And then the third, the in between, the middle subbundle EC, the center subbundle, should have a behavior which is in between those observed on the other two subbundles. So if you just compare how much the derivative expands a vector along EC, so the dilation ratio for a vector along EC, it should be definitely smaller than what you observe along the unstable subbundle, and definitely larger than what you observe along the stable. So the dilation rates along the center, dilation rates, plural, along the center subbundle are far away from those you observe on the stable and the unstable, and they are far away by a factor which is uniform. So this is kind of uniformly dominated behavior. That's what I mean by in between here for the center. Okay, the special case where there's no center is called uniformly hyperbolic. This is the classical theory that was developed starting with Stephen Smale and with fundamental contributions by Anosov and Sinai in the 1960s. At the end of the 1960s, it was becoming clear that this particular situation of uniformly hyperbolic dynamical systems was less successful than, less general than had been expected. Smale at some point conjectured that the generic dynamical system would be uniformly hyperbolic. That's not true. So in the 70s, there was a feverish search for generalizations of uniform hyperbolicity that could achieve the goal of being generic, of being very broad. All of them failed, but most of them died completely in the 70s. They were completely forgetful, except the one exception is partial hyperbolicity, which has remained relevant for a while, and starting in the 1990s became, in fact, quite active as a research field. The reasons for this are multiple. The partial hyperbolic dynamical systems have many of the geometric properties of uniformly hyperbolic maps, which means that they are it's possible to study them, to extend tools that were developed in the uniformly hyperbolic case to include this setting. On the other hand, they include many new interesting examples, many new interesting phenomena, and still are relatively restricted, protected setting where one can test ideas, conjectures that then hopefully will become relevant also in the general situation of dynamical systems. So I guess that those are some of the reasons why, starting from the mid-1990s, initially with with both conservative and non-conservative diffeomorphisms, this became a very important issue, a very important topic in dynamics. Now, one basic property, one basic fact about partial hyperbolicity, which is just where it starts to get interesting, is that partial hyperbolicity is an open property. If just because of uniformity, if you perturb a partially hyperbolic dynamical system, then any C1 perturbation is still partially hyperbolic, which means that whenever we give one example, in fact, we are giving a whole open sets of examples of such maps. So I will review very quickly some of the classical examples, because I will refer to some of them in the later part of the lecture. If you take a linear automorphism, a linear map in SLDZ, so matrix with integer coefficients, so D by D matrix with integer coefficients, and you assume that the spectrum has both eigenvalues with norm less than 1, eigenvalues with norm strictly larger than 1, but also some eigenvalues on the boundary on the unit circle in the complex plane. Then the map A induces on the torus, this just by going to the quotient, is partially hyperbolic, and so consequently any C1 perturbation is also partially hyperbolic. So this is one simple way of constructing partially hyperbolic maps. The second construction is by using flows. If one has an anosov flow, a uniformly hyperbolic flow, then by definition that means that the tangent space splits into an unstable subspace, which is uniformly expanded, another stable subbundle, which is uniformly contracted, and then, of course, the direction of the flow corresponding the direction of the vector field defined by the flow. And if instead of looking at the flow, you look at the corresponding time one map, then this time one map is partially hyperbolic with this as the partially hyperbolic decomposition with the direction of the vector field as its center subbundle. And a curious thing, I mean, a characteristic feature of this example is that the diffeomorphism comes immediately with a foliation, namely the foliation by orbits of the flow, a foliation which is tangent to the center subbundle and which is invariant under the diffeomorphism, the time one map. So I will come back to that. And not only that foliation is invariant, in fact, the leaves are fixed sets for the diffeomorphism for the time one map. Okay. Finally, the third and last kind of construction that I want to mention is by taking skew products. If you take, say, an anosov map on some manifold n, and then you consider this kind of skew product, where on the first coordinate you have the anosov map, and on the second coordinate, for example, a translation, a point-dependent translation on the torus, and here the torus could be replaced with other groups. So you just have a translation on the group, which may depend on the point, the first coordinate x. Then this is partially hyperbolic. The stable and unstable subbundles come from N, come from the Anosov, the diffeomorphism G on N, and the center direction is just the direction of the fibers, just the vertical direction along TD. Okay, there are now many other examples of partially hyperbolic diffeomorphism and other constructions, but these suffice for the kind of examples that I want to mention. So a classical fact that indeed it actually goes back to Anosov and Sinai in the uniformly hyperbolic setting, and was then extended by Breen and Piesin, and in a parallel way and in a much more abstract setting by Hish, Pugh, and Shu, is that the states that the stable and unstable subbundles of a partially hyperbolic diffeomorphism are uniquely integrable, that they have there exist unique foliations which are tangent to the two subbundles, to each one of the subbundles. There are unique foliations tangent to these subbundles, and these foliations are invariant in the set under the dynamics, in the sense that the diffeomorphism F maps the leaf through a point X to the leaf through the point F of X. So the leaves themselves are not invariant, but the foliation is invariant in the sense the dynamical system permutes leaves and maps leaves to leaves. And the key metric property of these foliations is that they are absolutely continuous. If you take cross sections to say the stable foliation and the unstable foliation, if you take two such cross sections, and then you consider, say, local small cross sections, and then you consider the map defined from sigma 1 to sigma 2 by sliding along the leaf, just moving along the leaf from one cross section to the other. That's called the local holonomy map. And those holonomy maps are absolutely continuous in the sense that the zero measure sets are mapped into zero measure sets. That these holonomies preserve the class of zero measure sets. This absolute continuity property is absolutely is the key ingredient in Anosov's major theorem, which states that the geodesic flow on a compact manifold is with negative curvature is ergodic. The argument Anosov used to prove this, it goes back to Hopf and was based in absolute and the property of absolute continuity. And one of the things that Anosov together with Sinai did was to, Hopf had done it in a context where the foliations are actually C1. For if you take the special case of a compact surface with negative curvature, then the relevant foliations for the corresponding geodesic flow are actually C1. And so we could use what we now call the Hopf argument quite easily. I mean, he had to invent the argument, but once he did, he could use it. And one of the major steps in moving from Hopf, from the case of surfaces to the general manifolds, was to replace regularity, smoothness, differentiability of the foliations by this weaker but still sufficient property of absolute continuity. So absolute continuity plays a key role if you want to do any sort of ergodic theory of these maps. And so it's quite important then that property of absolute continuity, which Anosov and Sinai proved for uniformly hyperbolic maps, the special case of uniform hyperbolicity, actually extends to these strong foliations of partially hyperbolic diffeomorphisms. Now, just in contrast to that, and that's where I start saying things specific to partial hyperbolicity, the center foliation of a partially hyperbolic diffeomorphism in general may not exist. And when it exists, it may not be unique. And when it exists and is unique, still it may not be absolutely continuous. And in fact, some of the results that follow suggest that absolute continuity is actually something quite rare for center foliations to have. It's actually quite difficult to get. This simplest setting where this question can be addressed and was addressed by people like, initially by people like Shub and Wilkinson, Ruel and Wilkinson, and others, is this simple construction, which is one special example of one of the constructions that I described before, the skew product construction. So you take an Anosov diffeomorphism, GA, actually an Anosov automorphism, a linear automorphism on the torus, GA, and you just multiply it by the identity, which is a very special case of group isometry on T1. And for example, if you want to fix ideas, you can think that GA is the so-called cat map of Arnold, I suppose, the linear automorphism induced by this particular matrix. But this is just to make the example as concrete as possible. Most of what I'm going to say is much more general than that. It only relies on the fact that we are doing this kind of skew product construction of a partially hyperbolic diffeomorphism. Now, in this particular case, first, the F0 has a center foliation, which one can easily find. The center foliation for F0 is just the foliation by vertical leaves. So the leaves, the center foliation is just formed by, the leaves are just of this form. So just vertical circles. And it follows from a general fact from Hirsch, Pugh, and Shub, foliation stability theorem, that if you perturb the diffeomorphism, any perturbation, any map which is C1 close to F0, besides being partially hyperbolic, which we already know is an open property, it also has a unique center foliation. And this foliation is conjugate to this one, which means that there's a homeomorphism sending the leaves of the center foliation of F to the leaves of the center foliation of F0. So when you start, you have this foliation by circles, just vertical circles. And when you perturb, you get something that pretty much looks like this, except that it's the image under homeomorphism. But in particular, the leaves are still topological circles. Now, to fix ideas, I'm going to suppose that F is volume preserving, so that I consider only perturbations that are volume preserving, which is the case for F0, obviously, because this matrix has determinant equal to 1, so GA preserves area on the torus, and then you multiply by the identity, which preserves length on T1. So F0 is volume preserving, and I'm going to consider only perturbations of F0 that are also volume preserving. And so this was the observation by Shub and Wilkinson back in 1999, I think. If you look at the center Lyapunov exponent of F, so the center Lyapunov exponent is just, you look at the dilation rate along the center. Okay, so just the norm, the center being one-dimensional, you can think of the derivative of along the center as being a number. A number is the dilation. And you take the logarithm. And you average that out with respect to volume. This is integral with respect to volume. okay? So this tells you on average whether the map along the center is mostly an expanding map, behaves mostly in an expanding fashion, or mostly in a contracting fashion corresponding to an average exponent which is respectively positive or negative. And Shube and Wilkinson observed, first of all, that if you calculate the exponent for f0, of course you get 0, because f0 is the identity along the center. So in that case, this function, for f0, this function is identically 0. But they proved that by small perturbations, you can find diffeomorphisms f arbitrarily close to f0, for which the exponent is not 0, for which the exponent is no longer vanished. So you can create a Lyapunov exponent by an arbitrarily small perturbation. And then, okay, that is perhaps not so surprising, although it's not really trivial to prove. It was not trivial to prove at the time. But what was more surprising, perhaps, was that then the center foliation cannot be absolutely continuous. If the exponent is different from 0, the center foliation cannot be absolutely continuous. And the ideology of the proof is not so difficult to understand. If you have a center exponent which is, say, positive, that means that it seems to mean that on most points the derivative along the center is positive, I mean, has a positive logarithm, and that would mean that under iteration by the map, you would expand vectors along the center. You would expand, and in particular, you would expand the length along the center. Now, that suggests that if you take a center leaf, which is a circle, and you start iterating it, typically it would be getting bigger and bigger, because the exponent is telling you that the map is mostly expanding along the center. So forward iterates of center leaves would tend to be longer and longer, have bigger length, which doesn't make sense because the family of center leaves consists of circles with bounded length. So how do you get out of this contradiction? Well, the mistake in this proof that I gave you is that, in fact, there are two notions of measure that appear. The fact that the exponent is different from 0 relates to volume. It says that it's an average with respect to volume. Whereas when I say that the dynamics would tend to increase length along the center leaves, I'm really talking about length, the length measure along leaves. So in order for this not to be a contradiction, volume, the measure volume on the torus has to be unrelated to the length measure along leaves. And this unrelation, this lack of dialogue between the two measures, is precisely what means not being absolutely continuous. The two measures are not, in particular, you cannot construct volume. You cannot construct a volume measure from the length measures along leaves, and which is precisely what not being absolutely continuous means. Okay. So sort of how nature manages to avoid a paradox in this situation. Just a few years later, maybe very few, Ruel and Wilkinson went further, and they proved that still in the same setting, although in fact it's actually more general, one can find a number k and a full volume subset of T3, which intersects every center leaf at exactly k points. So I put this, this picture was stolen from Amy Wilkinson's website, and it's a picture that illustrates in 2 dimensions the kind of phenomenon that Ruel and Wilkinson stated in their result, and which we now call atomic disintegration. So this is a picture of a foliation on the square, It's actually the torus if you identify the opposite sides. It's a foliation by circles of the torus. Each circle is a smooth circle. It's very, very smooth, in fact. And I think it's real analytic, each one of these circles. So at least infinity, for sure. And the property with this foliation is that there exists some set Z on this torus with which has full area. So area of Z is total, it's 1. And so this is the first property. And then Z intersected with each leaf consists of exactly 1 point. Okay, so there's some subset of this torus, or this square if you prefer, which has full volume, full area, and yet consists of exactly 1 point on each leaf. It's a very bizarre, from the metric point of view, very bizarre kind of metric behavior. And that's precisely what Ruel and Wilkinson were saying for the center foliation of these examples, that essentially, whenever the exponent is, the center exponent is non-zero, you have that there exists a full volume subset of T3, which consists of k points. It's not in the example, not necessarily 1, but which consists of exactly k points on each center leaf. And still, this set manages to have full volume on the ambient space. So this revealed that the behavior of center foliations can be actually quite wild. Not only not absolutely continuous, but in fact really as far from absolute continuity as you can imagine. Absolute continuity would tell us that we can calculate area by integrating length along the leaves and then integrating those results. It's kind of Fubini, a kind of Fubini theorem. You first calculate the length of the set along each leaf, and then you integrate that transversely to the leaves, and that should give you area. And well, no, it doesn't, because you can have full area with sets that on each leaf are reduced to a point. So as far away from Fubini as possible. So this is just what I just said. There exists a full area subset of the square consisting of exactly 1 point on each leaf. Okay, so that's the kind of one of the results that we were able to generalize to quite general setting, and in the process introducing some new tools for dealing with partially hyperbolic diffeomorphisms and their ergodic properties. This particular statement here is contained in the paper that is going to appear in the Katok Memorial issue of Ergodic Theory and Dynamical Systems. So it says, again, it's more general than this, but I'm focusing on one specific example just for being as concrete as possible. It says that if you take a small volume-preserving perturbation of F0, as I defined it before, the product of an Anosov of the Anosov cat map by the identity, then if the center foliation happens to be absolutely continuous, okay, if you have that, then your map is seeker a conjugate to a map of the original form. So if the center foliation, and we call it the rigidity property, rigidity theorem, because rigidity means, in dynamics, usually means that if you have some mild regularity, then you have a lot of regularity automatic. Just a little bit of regularity entails very strong regularity property, and that's the case here. Just assume that the center foliation is absolutely continuous. And then the conclusion is that your map, in fact, up to CK conjugacy is of this form. So up to CK conjugacy, your center foliation is actually a foliation of this form, a foliation whose leaves are vertical circles. Okay, so the center foliation being absolutely continuous implies that it is a CK foliation, that it is just the image of the trivial fibration by circles under a CK diffeomorphism, a CK conjugacy, as in here. Okay, so just this tiny little bit of regularity implies that the foliation is actually CK. And not only that, rigidity is not only at the level of the foliation, it's at the level of the dynamics itself. It means that essentially you did not change you almost did not perturb F0. You started with F0, which was a skew product of this type, a rotation extension of an Anosov diffeomorphism, and after perturbation, you have still a rotation extension by an Anosov diffeomorphism, although you may change the diffeomorphism a little bit, and you may change the rotation function a little bit, but that's up to CK conjugacy. That's the only thing you do. So it's very, very rigid situation, and that's the kind of statement I had in mind when I said that, in fact, in the real world of partial hyperbolicity, having center foliations which are absolutely continuous is actually quite unusual, quite special. I'm not writing down a statement of non-genericity, but this doesn't look very generic. I mean, it's just CK conjugate maps of rotation extensions that in this setting that have absolute continuity, absolutely continuous center foliation. Then there's another theorem which helps clarify the situation that we call the dichotomy theorem. It uses an additional hypothesis, and that's why I separated it. It assumes that the perturbation is accessible. So by accessible, as usual, one means that given any 2 points x and y on T3, you can move from one to the other by moving along pieces of path curves that are either contained on a stable leaf or sorry, this should be in fact so either contained in some leaf of the unstable foliation or of the stable foliation. Okay, so you can move from any point x on T3 to any point x y on T3 by a path which is whose legs, by a piecewise smooth path whose legs are contained either in the stable leaves or unstable leaves. And with this assumption, which is a rather mild assumption, in fact, that is now much better known, but for this we only need this old theorem of density, of genericity, that for the subset of perturbations of F which are accessible is an open and dense subset. So under this mild assumption, the dichotomy theorem says that there are two possibilities. Either the center foliation is absolutely continuous, that's one possibility, and we already know that is a rigid situation, or we have the Ruel-Wilkinson phenomenon that there exists a full volume subset that intersects every center leaf at exactly k points. So what Ruel and Wilkinson found is actually it looked bizarre when they found it, but it's actually quite common, because the only alternative, so this is precisely what I called what I call atomic disintegration. Okay, this is atomic disintegration, and the the only alternative to having an atomic disintegration is to have a center foliation which is absolutely continuous, and so in fact having a map which is CK conjugate to the origin to a rotation extension. So, except for this very slim family of maps which are CK conjugate to rotation extensions, the all the others have the center foliation has atomic disintegration, have this kind of pathological behavior, which looked pathological when Ruel and Wilkinson found it, but turns out to be, in fact, the main thing, the typical behavior.
Sorry,
okay.
Marcelo.
Yes.
Can I ask you something?
Sure.
Is there some result like this for other manifolds or only to torus?
No. This is true for any. I cannot give you the precise, but no, this is not specific for the torus. I wanted to give you a concrete construction of. So the assumption here, the key assumption is for this result, is that the center foliation is a foliation by circles. So I think this is called a Seifert bundle or something like that. So that's so it's important here that the center leaves are compact, first of all, and secondly, that they are one-dimensional. So in other words, that they are circles. But that's the main thing, okay? And the first factor, this factor here in particular, this here, we want it to be an Ozov, but it doesn't have to be an Ozov on the torus. It could be, in fact, anywhere. Okay, just
thank you,
and certainly not on T2. Okay.
Okay, thank you.
So I gave you. I recalled 3 very classical constructions of partially hyperbolic diffeomorphisms. One was through skew products. The other one through flows, and yet the other one through by using linear automorphisms on say on the torus, or more generally on manifolds, on nil manifolds, and the first set of results that I mentioned was for the skew product case. So now I move to the volume, to the flow construction, to the type of flow construction, and I will not address at all the third kind, the partially hyperbolic diffeomorphisms that are constructed as perturbations of linear automorphisms, or are in the isotopy class of a linear automorphism. The reason I'm not mentioning it is because A, the results are very different, B, the methods are very different, and C, the theory is much more incomplete. Still, there are some results in that setting. Again, I'm referring to the setting of partially hyperbolic diffeomorphisms of the derived from an Ozov type, for example, perturbations of linear automorphisms. Those have been studied by Regis Varão and then Ali Tazibi, and they have results in that setting too. Results that are different, in fact. That setting seems to be more difficult, and for that reason is less complete. But let me now say something about the flow case, and to fix both fix ideas. Again, I'm trying to be as concrete as possible, but also to give you the cleanest possible statements. I don't consider any Ozov flow. I mean, if you consider any Ozov flow, the time one map is partially hyperbolic, but I focus on one special construction of Ozov flows, namely time one maps of geodesic flows. Ozov flows were invented because of these guys, and I go back to the original setting of Hedlund, Hopf, and others. you take a surface with negative curvature, and you consider its geodesic flow, and then you consider the time one map to that geodesic flow. The Hopf theorem states that the geodesic flow on a surface with negative curvature is an another flow. You take the time one map, that gives you a partially hyperbolic diffeomorphism, and I take any perturbation, which is still a partially hyperbolic diffeomorphism. Okay, so this one of the three constructions, and then we have results that are kind of parallel to the previous ones. In the previous case referred to the skew product case, and as I told Luciana, answering Luciana, the key feature of those examples was that the center leaves are compact, where circles are compact manifolds. Now here, in the case of geodesic flow, the center leaves are, for the unperturbed map, the center leaves are just the trajectories of the flow, the trajectories of the geodesic flow. So essentially the geodesics. And those can be of two types. They can be closed, and in that case they are compact, but most geodesics are not closed. Okay, so in this case, this is very different from a geometric point of view. The center leaves here are a mixed bunch that includes typically a dense subset of periodic orbits, of periodic geodesics, and then, but still countable, dense but countable, and then the rest, which are just immersed submanifolds, immersed lines inside the unit tangent bundle of the surface. Okay, still the two kind of results that I mentioned before remain true in this case: rigidity and dichotomy. So in fact, here they are stated the other way around in the opposite order. First, dichotomy. Either the foliation is C-infinity, or there exists some full volume subset that intersects every center leaf at exactly one point. So either we have atomic disintegration, just as before. Either we have atomic disintegration, or the foliation is CK, and in this case K equals infinity. I'm just stating it because I mean, for the geodesic flow it's natural to think of it as being C infinity. Or the foliation is absolutely continuous, and in fact it is C infinity. So again, we have this dichotomy: either a lot of regularity or no regularity at all. Okay, either the thing is smooth, or you can find this kind of pathological behavior, metric behavior of Ruel-Wilkinson.
Does this perturbation have to be volume preserving?
Yes, sorry, I should have said it. Yes, this is yeah. Thank you very much. This is any volume preserving. We did some stuff for some things for non-volume preserving, but then the statements are a bit messier than this.
It's a mess. Okay. Thanks.
Okay, so this is for volume preserving. Yes, thank you. And then there's so this first item, this first part of the theorem is the dichotomy, and then the rigidity. If you don't have atomic disintegration, and thus you have a C-infinity center foliation, then it's because F itself is the time one map of a C1 flow. And the center foliation is actually formed by the trajectories of this C-infinity flow. So this is spectacularly sharp. Either the center foliation is as bad as it gets with this atomic disintegration, and if that doesn't happen, it just means that you started with the time one map of a flow, And you stay, your perturbation was such that you still have the time one map of a flow, of a C-infinity flow. And that the center foliation you are looking at, and you are very happy and very proud because you have a center foliation which doesn't have atomic disintegration. Well, you know, that's because you just picked a very special kind of dynamical system of the diffeomorphism, which is the time one map of a C-infinity flow. And this center foliation you are so proud about is formed by the trajectories of that flow. Okay, so this is extremely unusual, of course. The second, I mean, very few diffeomorphisms are time one maps of flows, and you even get all this regularity of C-infinity and so on. So one is dichotomy, and two is rigidity. So again, this has the ideological message that having absolutely continuous foliations is actually quite rare in this setting. Okay. Now I'm not going to say anything about the proofs, and I also realize that my time is running out. There's a whole lot of machinery that was developed by many people, in particular in works with Christian Bonatti, Javier Gomez Mont, Artur Avila, Jimmy Santamaria, and many others. I should add Ali Tazibi and other people. The both Rodriguez Hertz and Ures worked in this set. So the title mentions two issues. One issue is absolute continuity, the behavior of the center foliation, and now I want to address the second issue, which is related to it. It's the role of Lyapunov exponents, and it's clearly related because you saw in Puig-Schub that the way they found these pathological foliations was by perturbing the initial map in order to have a non-zero exponent, center exponent, the average center exponent, and then I wave my hands to explain why non-zero center exponent should imply a lack of absolute continuity. So let's look at that. In general, if the center direction has more than one dimension, then there may be more than one center exponent, and we call center exponents, plural, any expression of this type that you can get by using center vectors along the center subbundle. And these numbers are well defined almost everywhere by the multiplicative ergodic theorem. So one question is what Schub and Wilkinson did by hand with some ingenious elementary but very ingenious arguments, which is to perturb in order to create non-zero exponents. Can we always do that? And that's the kind of question that people, can we always perturb a dynamical system in order to make the center Lyapunov exponents different from zero? And that's something that people have looked at from various points of view. Of course, this was a question that Piesin himself was already asking in the 1970s. And I want to mention one result, which is quite curious of the way we are able to answer that question. So it's a construction that, again, is very classical. You can find it in the book of Hirsch, Puig, and Schub, the normal hyperbolicity lecture notes. You take a linear map of the R4 matrix, 4x4 matrix with integer coefficients and determinant equal to 1, and you look at the linear automorphism that it defines, it induces on the torus. The fact that A has determinant 1 ensures that FA preserves volume. It's something that you verify, not very profound. You have to check that A, regardless of which A, oh yeah, and you assume that there are two eigenvalues in the unit circle. So you want to do something that is partially hyperbolic, and you assume that one eigenvalue is expanding, another is contracting, and then there are two on the unit circle. And with that assumption, you can find the symplectic form that is preserved by A and by the induced diffeomorphism. And this is also classical. You can find it, for example, in Magné's ergodic theory book. If there are no, the eigenvalues of A include no roots of unit, then FA is ergodic. Okay, so this comes from general tools. And Hirschberg and Schub asked in 1977 whether, essentially, whether this FA was stably ergodic, whether it was volume preserving or even symplectic perturbations of FA are stably ergodic. And that turned out to be a very subtle problem, which was brilliantly solved by Federico Rodriguez-Hertz in his thesis. Yes, every volume-preserving diffeomorphism, which is close to FA, is ergodic. Now, we want to look at this from the point of view of looking at the Lyapunov exponents. And this map has, when we say it's partially hyperbolic, the unstable space is one-dimensional, the stable is one-dimensional, and then the center is two-dimensional because we assume that there are two eigenvalues in the unit circle, and then there's one inside the unit circle, unit disk, and the other one on the outside. So we want to look at this from the following point of view. Can we, when we perturb F, can we look at the center Lyapunov exponents, the exponents for the perturbations along this center subbundle, and can we make them different from zero? Can we turn FA, which the unperturbed map has zero exponents along the center? The exponents are basically the logarithms of these eigenvalues, and since of their norm, and since they are on the unit circle, the logarithm is zero. Can we perturb FA, and get an F whose exponents are different from zero? So we do that by, first by restricting to symplectic perturbations. Okay, we have the symplectic form here, which is preserved by FA. We fix that symplectic form, and we consider only perturbations that are symplectic with respect to that symplectic form. Okay, and the statement is that for any sufficiently small symplectic, sufficiently close symplectic diffeomorphism, one has again a dichotomy, two possibilities, and the first one is that the map is uniformly hyperbolic. So the first one is that, yes, the exponents became non-zero after the perturbation, okay? And the other one is that, in fact, we didn't perturb at all, that the new map is conjugate to the original one by a volume-preserving diffeomorphism, C1 diffeomorphism. I'm not sure we can get more than C1, we can prove more than C1, but at least that we can do. Again, this is something that has versions in higher dimensions. They are not quite as nice, so that's why I give you the lower dimensional statement. So either by perturbation, this is a very devious way of answering the question. Can we make the exponents non-zero? Well, you know, you try, and either you succeed, and if you don't succeed, I tell you that's because you didn't perturb your map at all. The new map is, in fact, still in the same conjugacy class. It's smoothly conjugate to the original one. Okay. Of course, that doesn't mean that given an F, it's easy to check in which of the two alternatives you are. Okay, it's not like you get an algorithm for making the exponents different from zero, but the theorem tells you that, yeah, either you do, or if you fail in doing it, that's because you, in fact, you're still in the same original dynamical system. And in either case, and this is a sort of an improvement to Federico's thesis, in either case, the perturbation is Bernoulli. Not only ergodic, it's Bernoulli. The reason is that FA itself is Bernoulli. That, again, is something that is in Magnier's book and then in most ergodic theory books. If there are no roots of unit as eigenvalues, the map is Bernoulli. So FA is Bernoulli, and F being conjugate by a volume-preserving diffeomorphism is also Bernoulli. Or in the other case, if all the exponents are non-zero, then that's classical results of Piessin and I think Ornstein and Weiss prove that non-uniformly hyperbolic systems are Bernoulli, up to some additional assumptions, a trivial kind of restriction that you can do. So, I mean, I should make it clear that this is, the setting is more restrictive than Federico's thesis. He assumed just volume preserving. This is for symplectic perturbations. But in the world of symplectic perturbations, we have ergodic, in fact, stably Bernoulli, the stable Bernoulli property. The way symplectic is used is in more than one way, but the main thing is that for symplectic diffeomorphisms, Lyapunov exponents have a certain symmetry. And in particular, the two center Lyapunov exponents are, in fact, symmetric to each other. So making them different from zero is easier. You just have to make one of them different from zero. And then the other will automatically be different from zero. You can pay attention to one of them only. Okay, so this is an example. I stop here, and it's an example of how the second issue, perturbing to make exponents different from zero, can be addressed. If I had an extra hour, I would be talking about the thesis of Carina Marin, where she who addressed that problem in a more general setting, a two-dimensional center, partially hyperbolic, but in a much more general setting than the one I'm describing here. Her result involves many different ideas that are not covered here at all, but that would be the next topic, just to say that this is really, these are just kind of appetizers to a much broader effort. And I don't want to abuse your time more and your patience. Thank you very much.
Thank you. Thank you very much, Marcelo. And well, there are questions, comments.
Is there, I will ask the same stupid question. Are you always going to be dealing with 2? Or do you have a feeling that 4 would ever be done?
Yeah, it depends on how honest you want my answer to be. Yes, I think your intuition is correct, and 4 should be the next step. But I'm not saying that the methods will give 4 easily. This you're right. This is pretty much, and now there's a little industry of dealing with partially hyperbolic diffeomorphisms whose center is two-dimensional. Not necessarily with the symplectic assumption, which is kind of cheating. It's turning 2 into 1. But there has been quite some development in the two-dimensional center case. But yes, I would hope that this doesn't have to be restricted to 2, in fact. But that doesn't mean I know how to do it or have any intelligent hints to give in public.
Excuse me, there is a question in the chat.
Yes, exactly. So I think Rafael Ruggiero is asking, what about moving the symplectic form in the last theorem?
Rafael, the honest answer is I didn't think about that at all, but I didn't think about the question that at all. Moving the symplectic form also means moving the volume measure, because in this case, the volume form is just the square of omega. Okay. So I should be careful because if you move the volume form, you know, exponents, Lyapunov exponents are things that are defined almost everywhere. And if you start changing what almost everywhere, where almost everywhere is, you might get into trouble. But definitely that's the question. I'm going to note it here. What about?
I mean, just perturb the symplectic form. The symplectic form. I mean, allow you to work for symplectic perturbations of the diffeomorphisms.
Yeah.
Okay. I mean, move, but not too much, because I mean, after what you said about the ideas of the proof, you have some rigidity of the eigenvalues. Okay, in any symplectic diffeomorphism, I mean, you have symmetries of the eigenvalues.
That's right. No, it's a very good point.
I mean, I don't know the details of your proof, but perhaps.
Yeah, no, it's definitely something worth looking into, and I will. I was more on the cautious side because it can fire back, but definitely, yeah, that's an excellent question. Definitely worth looking into. I said I will look into it, but if someone is interested in looking, please feel free to. It's a good question. It's a very good question.
There are any more questions, comments?
Yeah, can I ask, Marcelo, so you have this atomic decomposition that was very difficult to deal with, right? But there is this very strong thing that you have that for each leaf, the intersection has the same cardinality, if I understood. Yes, this one. You have exactly 1 point for every center leaf. And this is not a measured theoretical statement. It's really just one for every one of the centers. Yeah. So my question is about the regularity. For each leaf, you associate 1 point, right? For each leaf, you associate just 1 point. So the question is, can you say something about the regularity of this? For instance, you pick like a transversal section to the center foliation. You can associate with each point in this transversal 1 point in this special point. This is maybe his whole.
Danielle, I think I seem to remember. I'm not sure right now. Okay, so I see that this is being recorded, so it can be used in the court of law. So I will be cautious about my answer. I don't want to be sued on it.
I'm not going to tell everybody.
Yeah, this will be on YouTube the next minute. So with all these disclaimers, I think we know for general reasons that that section that you are trying to construct is non-measurable. Okay, so you want Hölder, I'm telling you, it's probably not measurable. I thought about that at some point. I don't right now recall exactly what were the conclusions, but I think in the books you find theorems like that.
I think the Milner had his paper about Fubini foil. I think he makes explicit the construction for a simple example.
Yeah.
So you can see it's some sort of selection process.
This picture that Amy Wilkinson has on her website is about Fubini foil. Is exactly about the construction that Milner describes in that paper. In the intelligence, which is these are conjugacy classes for maps of the circle. So it's exactly that situation. I think Amy did ran the computer program to draw these lines. And I think, yeah, I think out of general principles of this has a name. There's a whole theory about those things in the books, which is the theory came much before dynamics, much before realizing that those monsters actually exist in dynamics, which makes them very respectable monsters automatically. The section can, yeah, I mean, they were not invented. They are in the wild, so of course they are respectable. I had when I was an undergraduate, I had a course in topology which was full of counterexamples. One of the textbooks was this book called Counterexamples in Topology. And I remember there was one space which is connected. If you remove one point, it becomes completely disconnected. And that, of course, was a bizarre thing, connected space which becomes totally disconnected. And then my first paper was about some sets of the dynamics of the complex exponential map. And there comes an example. This was found by Devane of in the dynamics of the complex exponential map. There's such an example that shows up. So those things exist. But the theory, the general theory says, I think that the section cannot be measurable. This is really, we are in the, it's borderline of reality.
Borderline.
There are any other questions?
Can I just ask one last question, maybe? So
Sure.
in the example in the statement you mentioned, like maybe 2 pages down, you start with a geodesic flow. So the statement is also true for a NOSF, maybe with some assumption?
Yeah, I use this as a kind of a representative. The theorem here, so I emphasize that the first set of results were about the skew product construction, where the center leaves are compact, okay? This is kind of messed up from that point of view. There are leaves that are compact, they correspond to the closed geodesic, and leaves that are just immersed. On the other hand, this kind of construction has a special feature that is very peculiar, and that's that the center foliation is invariant, but this is an example of center fixing dynamics. Not only the center foliation is invariant, but in fact, each leaf is a fixed set. Because of course, if you take the time one map of a flow, the time one map preserves the orbits of the flow, okay? And when you perturb, the perturbations still fix. So this is the center fixing type of partially hyperbolic diffeomorphism. And so the actual theorem here is for center fixing partial hyperbolicity, okay? That's the key word. Center fixing means the case where the center leaves themselves are preserved by the diffeomorphism, okay? The third case, of which I said essentially nothing, apart from giving mentioning some names, is the perturbation of linear automorphism. There the leaves are immersed, not fixed, and it's really a different situation, which we understand less well. Okay, but this is really the key feature here is center fixing.
Okay, so any more comments?
Just one question.
Okay.
About this statement. I mean, is there anything special about the negative curvature or just for anosophy? I mean, what do you think about anosophy?
Well, anosophy is yeah.
I mean, take an anosophy geodesic flow on a compact surface, genus, homogeneous, and then.
Oh yeah, you can do for, yes, you can do for anosoph. The reason, Rafael, I stated it for the geodesic flow is the following, and let me tell you why. You remember that in the previous set of statements, at some point I introduced this notion of accessibility. Okay.
Yes.
And here on this page that you are seeing now, there's no mention to accessibility. The reason is that for geodesic flows, for timeline maps of geodesic flows, it's automatic that the perturbations will be accessible. That's the
so that's the only property you use.
Yeah, that makes the statement much nicer and but this, in fact, you can do this for timeline maps of any nodes of nodes of flow. As I said, the key thing is that you have center fixing, which is also the case there. Okay. So yeah.
Okay.
I should have said at the beginning. I did it in the middle that I picked the examples as simple as the very first non-trivial example of each situation, and I use that as a motivation.
Okay, then I think we can thanks Marcelo again for the beautiful lecture. Thank you.
Thank you very much.
Marcelo.
Thank you, Marcelo.
And perhaps Jacqueline, you want to say something about tomorrow? I don't know.
Well, just that we are back tomorrow for our last day at 11 Brasilia time, -3 UTC. So tomorrow we have a toast in the end of the day for celebrate our 50th anniversary, the 50th anniversary of our postgraduate program at UFRJ. So I hope everyone get ready. So if you don't have anything to toast, make sure that you have by 4 tomorrow. So let's thank all the speakers for the day and
thank you.
Thank
you very much.
Okay.
Bye-bye.
Bye-bye.
Bye-bye. Thank you for the talk.
Thank you, Marcelo.
Thank you, Marcelo. Bye-bye.
See you.
See you all tomorrow. Tchau, Vanessa. Ah, já foi. Então, até amanhã, pessoal. See you.